Hey everyone! In this video we will introduce some tools that we can use to describe relationships between two numerical variables. So let's jump in. We'll start by looking at tools we can use to review scatter plots. So things that we're looking for, what signifies a trend in the data. We'll talk about how to then measure that trend using the correlation. So we'll start with an example from a data set called the PREVENT data set. So we have data on demographic and cardiovascular risk factors. These were collected as part of the prevention of renal and vascular end-stage disease. So this data comes to us from the Netherlands. It's over a 10-year period, so we have a lot of data available here. We have information on variables such as the age at the beginning of the study, the gender, ethnicity, attained education level, a variable called RFTT, which we will come to shortly, and then various other health and demographic measures. So as people age, cognitive function changes over time. A test that can be used to measure that is something called the Rough Figural Fluency Test, or RFFT. This is designed to measure a person's abilities to plan, to multitask, to think ahead. Scores on this RFFT test range from 0 to 175 points. Now, looking at this data, is there a relationship between RFFT scores and age? Looks like in general, as age is increasing, RFFT score is decreasing. However, there is certainly a lot of variation in this data. Now, if we want to measure, say, what a relationship looks like, specifically what a linear relationship between two numerical variables looks like, we can use a measure called correlation. So correlation here refers to a measure of the strength and direction of a linear relationship between two numerical variables. So for us in statistics, correlation has a very particular meaning. We represent correlation with either an uppercase or lowercase letter r. Some references choose to use the uppercase, some use the lowercase. Correlation is what we will call a bounded measure. So it's defined on a narrow range between -1 and +1. So let's take a look at what different values of correlation might look like. So for example, if there is what we'll call an upward trend in the data, if as our x-axis is increasing, our y variable tends to increase as well, we'll say that there is a positive correlation. So here, correlation would in fact be greater than 0. If there is a negative trend or a downward trend in our data, so as x tends to increase, y tends to decrease, we say we have a negative correlation, and in fact, r is less than 0. Now, if there is no clear linear trend in our data, the points are just sort of scattered around in space, there may be no correlation. So let's take a look at some more examples of what different correlation values look like so we can get a feel for what correlation is really telling us. Take, for example, the endpoints here. We have a positive perfect correlation on the very left. We have a perfect negative correlation on the very right. In both of these cases, here and here, the points are all falling directly on a straight line. So if all of our points line up, we say that there is a perfect correlation, either positive if the trend is increasing, negative if the trend is decreasing. The farther we get from one, the more spread out points are around this linear trend line. However, we should still see sort of a linear shape. For example, this blue plot here has a positive correlation of 0.5. However, there's a lot of variability around that potential line as well. Same with -0.5 here in orange. Now, if there is no correlation, again, we're not really seeing either an increasing or decreasing trend. Now, the key thing to keep in mind here is that correlation measures a linear relationship. So it doesn't tell us much about, say, a curved relationship between two numerical variables. We should only use it when there is a linear trend potentially present. Again, the closer the absolute value of r is to +1, the stronger the relationship. R is greater than 0 when there is a positive association. R is negative, less than 0 when there is a negative association. Now, correlation can be misleading. What you're seeing here is a graph of a data set known as Anscombe's quartet. Now, these 4 data sets are special because they all have the same correlation, about 0.82. Now, looking at these 4 data sets, data set number 1 in the upper left is really the only one where correlation is an appropriate measure. We have a linear trend. The data is sort of following that straight line. If we look at, for example, data set 2 here in the upper right, the data is following a perfect relationship, a perfect trend, but it's not linear. This looks more like a quadratic curve. For data set 3 in the lower left, all of the points fall along a perfect straight line except for 1. And that one point that doesn't follow the trend is bringing the correlation down rather dramatically. With data set 4, the final data set, all of the points actually have no relationship. As y is increasing, nothing's happening to x. X is the same for all data points except for 1. Now again, all of these data sets have the same correlation. So the number, the value of correlation on its own doesn't necessarily indicate a strong linear relationship. Let's take a look at another data set. So in R, you can calculate the correlation between variables of a data set using the core function. Here we're using that $ notation once again. So you read this as variable x from the data set, variable y from the data set. So think of that $ as really reading as from. Now, this data set has a very small correlation, correlation R negative 0.06. So we might think there's nothing to this. There is, in fact, a relationship, and I picked this particular data set because it's kind of a fun one. This is what's called the Dino data set. There's clearly something happening in this. However, the correlation number suggests that there isn't. So what can we take away from these 2 examples? Well, strong correlations do not necessarily guarantee a linear relationship. We can still see high values for correlation even if the data isn't a linear trend. We can also see that weak correlations near 0, don't necessarily mean that there's nothing interesting in a plot. So I recommend that we never take correlation alone. We should always look at it along with scatter plots of our data. Now, let's take a look at some ways to make calculating and visualizing correlation go a little bit faster for us with the help of R. So one thing that we can do is calculate all pairwise correlations in a data set at once using what's called a correlation matrix. So here's how we might do this. In the PREVENT study, we have a lot of variables. Let's take a look at correlations between just a few. So we'll look at that RFFT score, the figural test score. We'll also look at a variable called VAT, which is a visual association test score. So again, a measure of mental perception. EGFR, this is a measure of kidney function. And then FRS, this is the Framingham risk score. This is the risk of a cardiovascular event or a heart attack. Now, in order to look at just these correlations, I'm going to start by creating a smaller subset of my data. So I'm going to create a new data set called PREVEN2. And this PREVEN2 data set is going to start by taking the PREVEN data set and then selecting only a few variables. So selecting specifically age, RFFT, VAT, BMI, EGFR or kidney function, and then the Framingham risk score. This isn't necessary, strictly speaking, as long as the variables that you're working with are numerical. If you try to calculate correlation with a categorical variable, R will throw an error back at you. So make sure that your data set has numerical variables. If it doesn't, you may need to select out only a few numerical variables. So then if we apply this core for correlation function to the entire PREVEN2 data set, what we get is a correlation matrix or a table. In order to read this, we look for where variables match up in the table. So for example, the correlation between the rough test score and age is negative 0.52. The correlation between the visual association score and age is negative 0.21. The correlation between BMI and kidney function is negative 0.128, and so on. So that's how we'll read values from this table. In this table, the strongest correlation that we can see is actually between age and risk score for a cardiovascular event. Those are highly correlated. Now, looking at that table itself gives us the raw numbers back, but that's not always very satisfying. We're humans, we like visual elements, so what can we do? We can visualize these correlations using a type of plot called a correlation plot. Now, this correlation plot comes to us from the core plot library in R, so we'll first load up this library using library core plot. I'll take my correlation matrix and save it in a new R object, just simply called matrix. And then I'll apply this core plot function to the correlation matrix. I do want to point out that this is not the only option. In fact, we'll see a second shortly, but these are two that I like in particular. So here is what is presented, or what is generated from this core plot. Now, looking at the diagonal element of this graph, what you're seeing here is that there's a perfect correlation between age and age. That's indicated by both the size of the circle. The size of the circle corresponds to the magnitude of the correlation. The color corresponds to the direction. So blue is a positive correlation, red is a negative correlation. So there's a perfect correlation between age and itself. That makes sense. There's a perfect correlation between all of the variables against themselves. We're going to pay special attention here to the off-diagonal elements. So for example, we know there's a strong relationship between age and the risk score for a heart attack. That's indicated by a relatively large blue circle. We also know that there's not much of a correlation between the kidney function, eGFR, and the body mass index. That's indicated by a relatively small, very lightly shaded circle. Now, another option that we can use is a correlation chart. The difference between this and a correlation plot is that the correlation chart includes scatter plots of the original data as well. This comes from another library in R called the Performance Analytics Library. So I will load that library up, and then I'll use a new function, chart.correlation. Notice that the C here with correlation is capitalized. Now this gives us something that looks a little bit different. There's a lot going on, so let's unpack this particular visualization. On the diagonal elements, what you're seeing are histograms of each individual variable. So this is the distribution of age in our data set. This is the distribution of our FFT, so visual test score, BMI, kidney function, and risk of a heart attack. On the lower diagonal elements, you're seeing scatter plots of each variable against itself. So this first one is the scatter plot of age and the rough figural test score. Down here at the bottom, we have age versus the Framingham risk score, and so on. So all of these scatter plots give us a quick way to see how the variables relate to each other. Now, these definitely aren't the prettiest looking scatter plots in the world, but they do the job for giving us a rough idea of what the data looks like. Now, on the upper diagonal, we have the correlations. The size of the font that's used corresponds to the size of the correlation. The asterisks here correspond to the p-value from a hypothesis test, specifically the hypothesis that the correlation is exactly equal to 0, or that there's no relationship. I wouldn't worry too much about the asterisks here for a few reasons. Without the p-value, it really doesn't tell us that much, just that we're below a particular threshold. I like to focus on just the magnitude and direction of the correlation alone. So let's take a look at another example here. We've got data from a study that was done to examine association between diet and blood plasma levels, specifically levels of beta-carotene and retinol. We had 315 observations on 16 variables. Looking at the names of the variables in this data set, a lot of these look like they will be numerical, but some might be categorical. For example, smoking status, that might be a yes-no variable. Prior smoking status, gender, those might be categorical. So we'll identify which rows contain numerical variables and create a new data set that just contains those. So in this data set, the numerical variables are age, catalase count, categories, fat, fiber, alcohol, cholesterol, beta-carotene in the diet, retinol in the diet, beta-carotene in the plasma, retinol in the plasma. Now, beta-carotene and retinol diet versus plasma levels, that's the relationship that we're really trying to target here. So we'll start with our correlation plot. Here I want to point out that you can use the pipe operator that we've learned previously to do this. So you can take your data set, send it through the core function that calculates the correlation matrix, and send that correlation matrix directly to plotting. So just another syntax that we can use here. Are there strong correlations between beta-carotene in the diet and beta-carotene in the plasma? Well, beta-carotene in the diet, beta-carotene in the plasma. Not really. There might be a small correlation. Let me move that yellow dot out of the way, but not too strong. Retinol in the plasma versus retinol in the diet as well. Not much of a relationship there between those variables. We do, however, see strong relationships or strong correlations between variables that we might expect. So variables like calorie content in the diet and fat content in the diet are highly correlated. Calories consumed and cholesterol, fat consumed and cholesterol. Those are sort of expected relationships in nutrition data, and they do, in fact, bear out in this data. So in the next few sets of videos, we'll start talking about some models that we can use to numerically describe the relationships between these variables. I'll see you then.